Welcome to this lecture on endocrinology. Today, we are going to explore a fascinating and crucial topic, hormone metabolism and half-life. Imagine sending a text message to wake up a friend. Once they are awake, you do not want their phone to keep buzzing endlessly. The human body works the exact same way. We will learn how the body deletes these chemical text messages once their job is done, ensuring our physiological systems remain in perfect balance. Now that we understand the basic premise, let us dive into what hormone metabolism actually is. Why does this concept matter so much? Think about adrenaline. If your body could not destroy adrenaline after a sudden scare, your heart would race endlessly and you would never calm down. Hormone metabolism refers to the specific biochemical processes that degrade, alter, or completely inactivate these hormones. By breaking them down, the body ensures that target organs can return to their normal resting state, preventing physiological chaos. Building on the idea of breaking down hormones, we must ask where this actually happens in the body. The heavy lifting is primarily done by two vital organs, the liver and the kidneys. The liver acts as a chemical processing plant, using specific enzymes to modify and degrade the hormones floating in your blood. Once they are broken down into safer, inactive products, the kidneys step in. They filter these remnants out of the bloodstream and excrete them safely into the urine. This continuous cleanup mechanism is absolutely essential for your survival. Knowing that the liver and kidneys clear hormones, we need a way to measure exactly how fast they do it. This brings us to a crucial concept called half-life, which endocrinologists use every day. But what is it? The half-life is defined as the exact amount of time it takes for the concentration of a hormone in your blood plasma to decrease by exactly 50%. For instance, if a specific hormone has a half-life of 10 minutes, it means that every 10 minutes, the remaining amount of that hormone in your bloodstream is cut perfectly in half. This idea of cutting the concentration in half repeatedly leads us to an important biological rule. Most hormones disappear from the bloodstream following what scientists call first-order kinetics. This simply means that the rate at which your body destroys the hormone is directly proportional to how much of it is currently floating in the blood. When you have a massive surge of a hormone, the body clears it out very quickly. But as the concentration drops, the clearance process naturally slows down. It is a continuous, smooth decay process, rather than a sudden drop. To represent this continuous, slowing decay process mathematically, we use the exponential decay formula. Let us look at where this comes from. Because the decay rate depends on the current amount, the mathematics naturally involve the constant E, which models continuous growth or decay in nature. In this equation, C of T is the concentration remaining at any given time. C0 is your starting concentration. The variable K is the elimination rate constant. If the liver starts working faster, this elimination rate K increases, and as a result, the hormone concentration will drop much more rapidly over time. While the exponential decay formula is powerful, doctors usually prefer to talk about half-life, because it is much easier to visualize in a clinical setting. This formula connects the two concepts. The half-life, T1/2, is equal to the natural logarithm of 2 divided by the elimination rate constant, K. The natural log of 2 is just a constant number, about 0.693. This formula tells us something profound. Half-life is inversely proportional to the elimination rate.
If your body's ability to clear the hormone increases, the half-life decreases, meaning the hormone vanishes much faster.
Before we move on to how we derived that formula, let us see this concept in action with a concrete medical example. Suppose a healthy pancreas secretes insulin, giving an initial concentration of 100 milliunits per liter. Insulin has a short half-life of 5 minutes. We want to know how much remains after 15 minutes. First, we figure out how many half-lives fit into 15 minutes, which is exactly 3. This means the concentration is cut in half 3 separate times. We multiply 100 by 1/2 to the third power, which is 1/8. The final answer is 12.5. Physically, this shows that insulin is cleared rapidly to prevent your blood sugar from dropping dangerously low. Now, let us look at a hormone that behaves very differently. Thyroxine, which regulates your baseline metabolism. We are given its long half-life of 7 days, and we need to find its elimination rate constant for a computer simulation. We choose our half-life formula because it directly links these two variables. By rearranging the formula, we see that the rate constant equals the natural log of 2 divided by the half-life. We substitute 0.693 and divide by 7 days. The result is approximately 0.099 per day. Physically, this means the body clears about 10% of the hormone each day, which is why missing a single pill does not cause immediate symptoms. Now that we have successfully used the half-life formula in our examples, let us understand exactly where it comes from. We are going to derive it directly from the exponential decay equation. Our goal in this first chunk of the proof is to set up the mathematical condition for a half-life. We know intuitively that at the exact moment the time equals the half-life, the current concentration must be exactly half of the starting concentration. So we write that the concentration at time t 1/2 equals C0 divided by 2. We then substitute this specific condition back into our main exponential equation. This sets the stage for us to solve for the time variable in the next step. Continuing from our setup, we now want to isolate the half-life variable. First, we can divide both sides by the initial concentration, C0, which cancels it out completely. This makes sense intuitively. The half-life does not depend on how much hormone you started with. Next, to get our time variable out of the exponent, we take the natural logarithm of both sides. The natural log of 1/2 simplifies to negative natural log of 2. Finally, the negative signs cancel out, and we divide by the elimination rate constant K. And there we have it, our final result. We have mathematically proven that the half-life is simply the natural log of 2 divided by the elimination rate. To visually reinforce what we just learned and proven, let us look at this exponential decay curve. On the vertical axis, we have the hormone concentration as a percentage, starting at a full 100%. On the horizontal axis, we are tracking time, but specifically measured in multiples of the half-life. Notice the smooth blue curve. At time 0, we are at 100%. After exactly 1 half-life, follow the dashed line, the concentration drops to 50%. After 2 half-lives, it halves again to 25%, and so on. This diagram perfectly illustrates the first-order kinetics we discussed, showing how the absolute amount of hormone removed gets smaller as the concentration drops. We have covered a lot of ground today, so let us summarize the most important ideas. First, hormone metabolism is your body's essential cleanup mechanism, ensuring chemical signals do not overstay their welcome. Second, The half-life provides a simple, measurable way to track this decay, telling us exactly how long it takes for half the hormone to disappear. Finally, remember that the length of the half-life dictates the hormone's function. Short half-lives, like insulin, give rapid minute-to-minute control, while long ones, like thyroxine, offer stable, long-lasting regulation. You now have a solid understanding of how doctors use these concepts to time life-saving therapies perfectly.